Okay, so we are going to do a real quick little video on the first section of chapter 2 today. So let's go ahead and get this loaded up here. All right, so you can see these are our sections of chapter 2 that we'll be talking about. Today we are going to focus on the first one, and that is describing motion. All right, so the first thing we need to talk about when we talk about describing motion is that we must have a frame of reference. And when we talk about a frame of reference, we're just talking about our position in the universe, our position on Earth, our position of wherever we are. So before we start talking about motion and moving from one place to the other, we have to talk about where are we to start with. And for us, that is going to be a coordinate system. So basically, your XY graph is going to be our frame of reference. And when we talk about motion in one dimension, we are just going to be talking about motion along that x-axis. That is our one dimension. And the origin of where you're going to start, that's always going to be the origin on that graph, or a value of x equals 0. Okay. Once you have the origin and you have a positive direction, so we know that if this is our coordinate system, and here is our origin, that's our 0 point, then if we move to the right, that's going to be a positive direction. If we move to the left, that's going to be a negative direction. So once we have that chosen and established, then we have to use that consistently throughout that problem. Okay. So we have set up that our frame of reference is the x-axis. When we're talking about one-dimensional motion, it's just going to be the x-axis. And of course, we'll use the letter x to label that position. And when we draw an arrow from the origin, so again, here's our x-axis. Let's say that is our origin. So what we do to show our position is we draw an arrow from the origin to the object, wherever the object is. So let's say that's our object. So we draw an arrow from here to here. Then that is what we call our position vector. It gives us a direction, but it also gives us a magnitude of how far you are. Whenever the object is in motion, its position is changing. So as long as that object is sitting still, then we can know its position. But once it starts to move, then obviously its position will also change. So let's look at some examples. We have initial and final positions. We always indicate our initial position with an XI for initial and our final position with an XF for final. So let's say this is our position vector. So here is our original starting point at 0. Here, that's our origin, at 0. This is our starting point at XI, that's your initial position, and this is where he ends up at XF. And so the distance from the origin to wherever he's going to wind up ending up is going to be designated with that arrow, and the head of the arrow shows what direction he's walking in. So distance is the total length of the path taken on a trip. Total length. Distance is the total length. There is no direction associated with the distance. So since there is no direction, we call that a scalar quantity. Now this is going to get confusing in a minute because we're talking about distance right now. In a few minutes, we'll be talking about displacement. But for distance, that is a scalar quantity and is just the total length of the path taken. We use meters because in everything we're using the MKS system, so that's meters, kilograms, and seconds. All right. So displacement, on the other hand. So they both start with D. They're both going to use the letter X in some situations, so that's why it can get confusing. So make sure you keep these straight in your notes. So displacement is the change in an object's position, and it is a vector. It has a magnitude and a direction. So you have to give it a number value, and then you have to tell what direction it's going in, like north, south, east, or west. Its unit is still going to be meters, but the sign of the displacement indicates the direction of motion. So motion in the positive direction would have a positive value. Motion in the negative direction would have a negative value. So make sure you're keeping those straight and just picture that horizontal axis in your mind with the origin at the middle. And so if you're moving to the right, that would be a positive position. Moving to the left, be a negative position. Displacement. Okay, so here's some more examples using displacement. So we always represent displacement with not just an x, but a delta x, because displacement is not just distance, it's the change in distance. And that delta is always written as the final minus the initial. That's what it always means. So delta x is the same thing as saying xf minus xi. So delta x is positive when a change in the position, the change in position is in the positive direction, and it's negative when the change in position is in the negative direction. So if we look at our examples, here's our starting point, 0, and here's her initial position. If she continues to run to the right and the numbers continue to get bigger and bigger and bigger, well, that was going to wind up being 6 meters for her final position because she ran in the positive x direction. And then if we look at the other situation, here's our still the same origin and the same distances, but this time she's running in the opposite direction. She's running in the opposite direction. So her change in displacement this time will be negative 4 meters, whereas before it was positive 4 meters. Okay. Okay, so some things to remember as far as differences between distance and displacement. Distance is the total length traveled, whereas displacement is just the net change in position. An object's displacement can be 0. So if you have something that returns right back to its starting position, that means that its displacement is 0. Even though it may have traveled a really long way, its displacement or its change in velocity is still going to be 0. Okay, so here's another example of the kind of stuff we're talking about. I'll leave it alone. It doesn't seem to want to move now. All right, so the total length going from the math class to the library and then to the physics room. So here's the library. That's our starting point. So we got 5 meters to the physics room and then an additional 3 meters to the math room. So that's 8 altogether. And then we're going all the way. Oh, wait, no, that was it. Total length traveled in going from math class to the library and then, oh, okay. Let's start over here. All right, so let's try this again. Total length travel and going from the math class, we're going to start here to the library. So math to library is 8 meters. And then to the physics room. So that's 8 plus another 5 meters to the physics room. That's going to give us 13 meters as our displacement. Now, or as our distance. That's our total length traveled. Then it says to find the displacement. So the total length or the distance traveled is 13 meters. And so now let's look at what the displacement is. All right. So you're going from math to the library. So again, that's going to be 8 meters. And then it says to go from the library to the physics room. Okay, that's going to be 5 meters off, 5 meters less than what you would use than what you might be used to, because you're going in the opposite direction. Okay, so 8 to 0 would be 8 meters plus 5 meters, but you're going back in the opposite. No, that's right. Never mind. So -8 plus 5 is -3 meters. Okay, and I think that's it for today. Yep, that's it. All right.